All right, warm-up number one, we gotta find the magnitude is 6, and we want it to be in the same direction as -2, 5. So to capture the direction, I'm just gonna find the unit vector. Remember, it's just a vector with a length of 1, and it captures the direction for us. We find it by just finding the current length of this vector. So the current length of this vector is 2 squared plus 5 squared, so that's the square root of 29. So I'm going to get that this new vector is going to be 6 times the unit vector that we just found, which I guess I didn't actually write it yet, but it's -2 over the square root of 29 and 5 over the square root of 29. So I'm just multiplying 6 by that. All right, so just -12 over the square root of 29. You don't need to rationalize. 30 over the square root of 29. For example 2, find the magnitude and direction angle of this vector. So magnitude, that's pretty straightforward, right? I'm just going to be doing 3 squared plus 8 squared. So the magnitude of this vector is going to be the square root of 73. Now for the direction, a couple things we got to pay attention to. First is that this is in quadrant 2, and I know that because -x, +y, so I know that this vector is pointing this way. So when it asks for the direction, this is what I'm looking for, but what I'm actually going to find is this first, so a little reference angle. So I'll do tan inverse of the y over the x value, and doing that in my calculator, what did I get? 69.44 degrees. Alright, so in order for me to find that actual angle, because this is our reference angle, if I'm in quadrant 2, what I need to do is go to 180 and then subtract the reference angle. Okay, so theta as a direction angle is going to equal, in this case, 180 minus theta as a reference angle, which is going to be 110.6 degrees. Vector multiplication, we have two different ways that we can actually multiply vectors. One's called the dot product and one's called the cross product. For the cross product, if I had two different vectors, let's just say I had these two vectors, and I multiplied using this cross product, what it actually gives me is this vector. That's actually in the third dimension. And we don't really do things in 3 dimensions in this class, so we're just not going to use the cross product at all because we don't want to deal with this 3-dimensional vector. So we're going to deal with a dot product. And when we do a dot product, it actually just gives us a real number. And the formula for it is really straightforward. If I have two vectors, so I'm going to use vector u with u1 and u2 to represent its values, and v, I don't know why we use letters that look really similar. It's probably not the smartest idea in the world, but if I do u dot v, and that's how we say it, so we don't actually say that we're multiplying, we say u dot v, because if we were doing cross product, we would have to say u cross v. So if we're doing u dot v, very straightforward. Take the x values, multiply them together, take the y values, multiply them together, and then add them. So that's u1 times v1 plus u2 times v2. And this is a formula that you need to memorize, but it's not super difficult, I think. So I'm pretty sure you can handle it. All right, so we got some properties for the dot product that we can use, which is going to just be, if you do the dot product of u dot v, that's equal to the dot product of v dot u. Pretty straightforward. This one's kind of a neat property. If you do the dot product of itself, it actually equals the magnitude squared. And we're going to be using that a little bit later on, this property. If we do the 0 vector times with the dot product of u, we just get the 0 vector again. And then just some other ones that we're probably not going to use too often in this class, but if I were to do something like u dot product of 2 other vectors that are added together, that I can kind of distribute and do the dot product of u and v, and then add that with the dot product of u and w. And I can also reverse that, and I could do something like u plus v and then dot product w, same exact idea, it works. And then the last one that we'll talk about is if I have some sort of constant multiplied by a vector and then doing the dot product, that it doesn't really matter where I put this constant, I'll end up getting the same thing. So I could actually move it to the second vector if it was easier to work with, or I could actually find the dot product first and then multiply by the constant, which is probably what I would do if I was doing this. For example 1, we're just going to apply the dot product formula to it. So I'm just going to do 3 times 5, and I'll do it kind of long-winded, especially this first time. So 3 times 5 plus 4 times 2. So that's going to be 15 plus 8, which is 23, the last time I checked. So same idea, 1 times negative 4, and then I'm going to add that with negative 2 times 3, so negative 6, so I get negative 10. And then here what I would do, until you get used to dealing with the i's and j's, is maybe convert it back into the traditional vectors. Remember, we just literally pull the numbers in front of the i's and j's out, and now I can just do 2 times 3 and get 6, and then add that with negative 1 times negative 5, which is positive 5, so I get 11. And then once you get kind of used to this stuff, you're going to realize that you can ignore the i's and the j's, and you don't need to put it in standard notation. Definitely no I squareds or j squareds. That's bad, don't do that. Some of you want to, I can tell. For example 2, they want us to just use the dot product to find the magnitude, so I'm just going to use that other property over here. So I'll write it out just to be really explicit. You probably wouldn't use this realistically. We're going to use it in the next step, so it's just making you practice it so that you kind of see that it's a thing. But if I do 4 times 4, I'm going to get 16, negative 3 times negative 3, that's going to be 9, and then I'm going to get 25, and according to this, that's the magnitude squared. So I'm just going to square root everything, and magnitude, for now, has to be positive. In other chapters, we'll deal with kind of negative stuff. We can also just check this, right? So we know how to find this. We know that it's just the square root of a squared plus b squared. So if I do that, I have 4 squared plus negative 3 squared, and I get big old square root of 16 plus 9, and I get the exact same answer. So this property is a real thing. It actually works, and we're going to use it in the next exploration. All right, so for this first exploration, what we're looking for is to actually try to come up with a formula to find this angle in between two vectors. We've talked about before how vector addition is kind of this vector that's right here in between them, but there's also vector subtraction can be visualized, and it would actually be going this way. So this is v minus u. And it's not super important that you understand why that works, so I'm not going to really go into great detail. But this forms a triangle where the magnitudes are the lengths of each triangle. So I can actually set up a law of cosine situation here. And just to remind you what that is, that's law of cosines. So I'm going to let this side be A, and then it really doesn't matter what I let be B and C, but I'm going to have the magnitude of v minus u squared is going to equal the magnitude of v squared plus the magnitude of u squared minus 2 times the magnitude v, magnitude u, cosine theta. Whew, that was a lot. But for this one here, I'm actually going to go backwards. I have magnitude squared. I'm going to rewrite it as dot product. So I can say that this is really v minus u dot v minus u. Okay, and it just equals all that stuff. I'm just not going to write it out right this second. And what I can actually do is FOIL. So foiling still works with the dot product. So I can do v times v, or v dot v, and then I'll have 2u dot v for when I do the OI in FOIL, and then I'll have a minus minus uu, so it'll be plus u dot u, and that equals all of that stuff. And v dot v, well, that's just the magnitude of v actually, squared. and u dot u is the magnitude of u squared. So now I'll rewrite these things out here. I have v squared plus u squared minus 2 magnitude u. I'm going to run out of room. Oh no. And I hope that you've seen that some things might cancel out now. So all of that cancels out. And I'll write like a nice little clean line here of what it is that we're kind of left with. I'm hoping that you maybe notice that these 2's are going to cancel each other out as well. And all I'm going to do is just divide these to the other side. So I'll have that cosine theta, after I've divided these away, is going to equal the dot product of u dot v over their magnitudes multiplied together. And we can use this formula to find the angle in between by just doing cosine inverse of it. So this is the formula that we're going to have to memorize. Now let's try using this angle in between formula. We're going to try to find the angle in between vectors u and v. So the first thing I'm going to do is just find their magnitudes. So the magnitude of u is going to be 2 squared plus 1 squared and the square root of that, so that's 5. The magnitude of v, 1 squared plus 3 squared, so that's going to be 10. So now I'm just going to use the formula. So I have cosine theta equals the dot product, so the x's added with the y's multiplied together, so 2 times negative 1, and I'll write it out long-winded for us so that we can see it this first time, and then I just divide by their magnitudes multiplied by each other. So that's going to give me cosine theta equals, let's see, negative 2 plus negative 3, so negative 5 over the square root of 50. And remember, we can multiply the insides of square roots together. And I can simplify as well. There's 25 in there. I can pull it out as a 5, so I'll be left with the square root of 2. So I end up getting that this is actually a negative square root of 2 over 2. So I'm going to try to figure out, well, all right, if cosine theta equals a negative square root of 2 over 2, let's see, it's negative, so it's going to be over here, and that's going to be when it's a 45. So what is the actual angle then? And that's going to be 135. So the angle in between these two vectors, this one and this one, is going to be 135 degrees. We'll do that again this time. This time we'll need a calculator to help us figure it out. But I'm going to have cosine theta equals dot products, so that's going to be negative 4 plus 15 over their magnitudes. So this is going to be square root of 13, and this one's going to be square root of 29. So I'll just simplify that a little bit. That gives me positive 11 over the square root of some ginormous number. I can just type 13 times 29 in the calculator when I'm doing it very carefully. So theta is just going to equal cosine inverse, whatever this is, 11 over the square root of 13 times 29. And I'll just type that directly into my calculator. I'm going to be in degree mode right this second, so 55.49 degrees. So the angle in between these two vectors is 55.49 degrees. Vocab time. We got this vocabulary word here called orthogonal vectors. And basically, orthogonal vectors are just going to be vectors that the angle in between is going to equal 90 degrees. Okay? So I know what you're saying. You're like, why don't we just call it perpendicular vectors? That kind of makes sense, right? If I have two vectors, and as long as they form 90 degrees, why wouldn't we call them perpendicular? And essentially, it's a technicality. So if I were to do the zero vector, which is just a vector that has no direction and no length, it's actually perpendicular, so forms 90 degrees with every single vector in the world. And so we came up with this other word, orthogonal, that basically excludes the zero vector. So by definition, orthogonal vectors can't be the zero vector. So that's just kind of that. We get some cool properties that we can do that make it shortcuts for us to figure out whether or not they're orthogonal or not using the angle in between formula. So if they are orthogonal, that means the angle in between is 90. And so we know that they have to follow this pattern, okay? Because we just showed that that was true. But what does cosine of 90 equal? So let's see, that's the x value when we're up here, and the x value when we're up there is 0. So I know this has to equal 0. And what's the only way a fraction can equal 0? If the top equals 0. So if the dot product ever equals 0, then we know that the angle in between has to be 90. So it's like a fun little property that we can use to help us kind of check whether things are orthogonal or not. For example 4, we've been asked to prove that vector u, which equals 2, 3, and vector v, which equals negative 6, 4, are orthogonal. Now, because they've asked us to prove it, we actually have to do a little bit more work. If they just wanted us to decide whether it was or not, we could do something different, and I'll kind of show you that at the end. But basically, if I'm trying to prove that they're orthogonal, I'm just going to use this property right here, which says if their dot products equal 0, then that automatically means that the angle in between has to be 90. So I'm just going to first find the dot product. So 2 times negative 6 is going to be negative 12, plus 3 times 4 is positive 12, and I get 0. So because that equals 0, and this property exists, I know that these two vectors are orthogonal. Now, if I'm looking for a shortcut to try to just figure out whether they are without actually proving or really showing, just determine whether they are orthogonal or not, I can actually jump back to what we did on Vectors Day 2, where we had that challenge example in the practice problems, where you were using slopes, and we basically turned slopes into vectors. Well, we can do the exact opposite. I can say that the kind of slope, we'll say, of u is going to just be y over x, and that the slope of v is going to be y over x, so that's going to be 4 over negative 6, and if I reduce that, that's negative 2/3, and these are opposite reciprocals, which means that they are perpendicular, aka orthogonal. We could also prove that two vectors were parallel if their slopes were equal. Example 5, same thing. We just want to decide whether or not they're orthogonal, so we can just use the dot product formula. So negative 4 times 1 is going to be negative 4. Negative 1 times negative 4, positive 4, equals 0, so they are in fact orthogonal. We can also use our little shortcut that we just learned. So the slope of u is going to be the y value over the x value, and the slope of v, y value over the x value, and these are opposite reciprocals, which means that they are perpendicular, aka orthogonal. Now, for example 6, I'm not actually going to bother showing you the work. If you're super interested in it, what it basically does is proves a property in geometry that you probably have forgotten, but there was some property that you had way back in geometry that said if you have a diameter and you have any 2 points and then a third one on this line, and this one can be moving, that the angle that's formed, as long as you're connecting back to the points that the diameter intersects the circle at, this angle will always be 90. And that was some property you learned way back in geometry, and we can prove that that's true in vectors. So that's all example 6 is doing. You don't need to do it or know it. It won't be on any tests. It's just kind of a neat application that connects it back to some math that you did a long time ago. Woo!